Thank you. So I was tasked by the organisers to talk about the evolution of dynamics of disks and ExoZodi. And although there's lots of interesting things on the evolution and dynamics of protoplanetary disks, like the kind of objects that Meredith was talking about, that's not what I assume that I've been asked to talk about. I'm going to talk about disks being debris disks. So my interpretation of what a debris disk is it's basically anything that you see around a main sequence star that isn't a planet. So with the help of this artist's impression, we've got rocks and planetesimals and maybe comets and the dust and gas that may come from them. And in that view of debris disks, ExoZodis are just a subset of debris disks. But the reason why I assume I've been asked to include that in the title specifically is because the debris disks that we generally think about are these ones that are large and far away from the star. And these are relevant for imaging of planets, the planets that have been imaged at the moment. But in the future, when we want to image Earth-like planets, then we'll need to understand the dust that's closer to the star. And by ExoZodi, my interpretation of ExoZodi is that it's dust that is close to the star, and specifically at a location which is around the temperature of the Earth. So it's the kind of dust that might cause problems when you try and image Earth-like planets. Okay, so we don't have the artist's view of most systems. This is what we have, as Jean-Charles was saying. We work with broadband photometric information, so we have the spectrum of emission from the star. Of course, here we've got the star, and then we've got this extra emission from dust that's orbiting the star. And for stars that are near enough and their disks are bright enough, their disks can be imaged. So this is the star Fomalhaut seen in photometric light, and this is an image of its disk. And this shows that the dust is confined to a ring that's at about 130 AU in radius. And in fact, most debris disks look fairly similar in the sense that they have fairly empty inner holes in the inner regions. And our solar system biased view lets us look at this and go, aha, there's probably a planetary system sitting in the middle of this region, which is why it's empty. In the case of Fomalhaut, there's even a planet that has been, or planet-like object that has been detected in there. Because if you look at the solar system, then you see that we have a whole bunch of planets in the inner region. This is Jupiter out to Neptune. And outside of that, we have a belt of planetesimals in the Kuiper belt, which are presumably grinding down into dust. So the solar system would look something like Fomalhaut if we could look at it from the outside, and with some caveats that it would also have to be brighter and bigger to look exactly like Fomalhaut. And this is the view that I'm going to take in this talk, that we can think of debris disks as being just a component of the planetary system. There are other ways of looking at debris disks that are equally valid. You can take a step back and say, well, actually, do we know if there really are planets in the system at all? Perhaps debris disks are just some kind of descendant of the protoplanetary disk, and the dust that we're seeing and the planetesimals could have nothing to do with planets. That's a totally valid view, but I'm not going to take that perspective here because we're in a workshop talking about imaging planets, so we have some kind of bias in there that we want to know about how these things interact with planets. Anyway. Okay, so I'm going to start off by giving you some primer about the physics of debris disks. And in fact, I'm going to start off by talking nothing about planets, because to understand this physics, we have to understand fundamentally what's going on within them and how that affects what we see. So I'm going to start off with a kind of fairly general overview of the physics of debris disk, and then I'll get on towards the end. Hopefully I won't take up too much time, so I'll be able to get on and talk more specifically about ExoZodis. So the simplest view of a debris disk is that we have a ring of planetesimals. They're all orbiting the star. Basically, the planetesimals, all they do is they orbit the star on Keplerian motion, and that's all they do. And the biggest perturbation they have is when they collide with another planetesimal. When they collide with another planetesimal, they get broken up into a bunch of boulders, which then orbit the star, doing nothing until they collide with other boulders, and then get broken up into rocks that collide and get broken up into pebbles that collide, get broken up into sand-sized objects, into smoke-sized dust, into tiny micron-sized dust. That whole process is called a collisional cascade, whereby this is the number of objects as a function of size. Mass is passing down the collisional cascade from the biggest objects down to the dust. And as a result of that process, you expect to have, as been mentioned already, a characteristic size distribution that has a slope of about 3.5, and what you need to remember from this is that most of the mass is in the biggest objects, and most of the area, which is what you see, is in the smallest dust. So that's mostly what's going on. But when you get down to the small sizes, then the dust gets affected by interaction with radiation from the star, and the force of that radiation force is usually characterized by this beta parameter. This is the ratio of the gravitational force to the gravitational attraction of the star. That's because the radiation force falls off as 1 over r squared, as does gravity, so this beta parameter is independent of distance from the star, and it's roughly 1 over the diameter of the particle in microns. So you have particles that are 1 micron in size, see the same gravity, same radiation force as the force of the star, so essentially they see no gravity from the star. So the effect of this is to basically see a smaller mass star. And what this means is that if you have a planetesimal and it's on a circular orbit, it gets broken up at this point here, then dust with of different sizes that have a different beta, as shown with their subsequent orbits, are shown by these lines here. If beta is greater than 0.5, then the dust gets put immediately onto a hyperbolic orbit. It just goes straight out of the system. And this is what basically truncates the collisional cascade. Mass is flowing down the collisional cascade till you get to this micron size, at which point dust gets blown out. And that means that if you're looking at the surface density, we have all the planetesimals as a function of distance. Planetesimals will be bound into this ring, but you'll have a flow of mass going outwards. But this dust which is flowing outwards is usually not going to be very bright, because it just goes out at the velocity at which it started, pretty much. But you do get to see this halo of dust just outside the belt, because all the dust that remains weakly bound to the star gets put on these orbits that are highly elliptical. And what this means is that when you look at debris disks, if you can observe these small dust grains, and that's what you see, you're sensitive to cross-sectional area, most of the cross-sectional area is in small grains, then you see the halo of dust extending out beyond where the planetesimal belt is. So when you look at images like this, which is at AUMIC that Debbie was showing us, lots of images like this. This is an edge-on debris disk. The dust is seen in scattered light going out to hundreds of AU. This doesn't mean that this star has a Kuiper belt that goes out to hundreds of AU. The Kuiper belt in this system is in at about 30, 40 AU in a fairly narrow radial range compared to the way it's seen. But all we see out here is just very small micron-sized dust that's put on these highly elliptical orbits. So that's a caution in the interpretation of the observations. Now, the radiation pressure is just the radial component of the force. There's a tangential component as well, and that causes drag, which makes the dust, which starts off in the belt, it pulls it inwards. So rather than going outwards, it pulls it inwards. Now, normally we don't have to worry about this when we look at debris disks, because they're very dense, and that means that collisions happen so frequently that dust passes down small enough that it gets blown out by radiation pressure before it has a chance to migrate inwards. If you have a low-density belt, however, then no collisions can occur, and the dust can make it all the way into the star, where it would sublimate or get accreted onto the star before it has a chance to collide, in which case the mass loss is inwards. And this is what happens in the solar system. So we saw a few of these kind of zodiacal light images before. The Earth is sitting in the middle of this tenuous cloud of dust, because dust is created in the asteroid belt and just sweeps past the Earth without suffering a collision. But that's because the asteroid belt is fairly low density, and it has hitherto been thought that we don't really have to worry about PR drag in extrasolar debris disks. But I'm going to come back to this point, so hold this point in your mind, and I'll come back to it later, because we're realizing that PR drag can be important in some disks. So let's put all of those pieces together. This is the most simple model, remember, that we can have of a debris disk, wherein we're just taking account of collisions and radiation radiation pressure and PR drag. And if we have a model where we have the number of things, well, this is cross-sectional area rather than number as a function of size, and we put all of our material into, we're going to forget about the radial component, we'll put everything into a one-dimensional model and start off with the size distribution that we expect analytically, the 3.5 power law, and say, how does that evolve in time? Well, we can do that because we can work out how often things in this bin here collide with things that are in that bin, and people have thrown rocks together either in the laboratory or in a computer to work out what happens, how many fragments are made, and you can put those into this model and work out how it evolves forward with time. This time is going to be going up here logarithmically, so don't worry, it will go faster. And you get something that ends up looking like this. And we understand all the features in this quite well, and that people study this. It's still a very active area of study because people take these size distributions that you get and compare them with the asteroids, the size distribution of asteroids and Kuiper belt objects. But we get a slope that's slightly steeper because we know that smaller rocks are stronger than larger rocks. We get a turnover here to become a flatter size distribution because when you go to even very big things, bigger than a kilometer, then they get strengthened by their self-gravity. You get a few waves here because of the fact that the cascade is truncated. And if we let this evolve, keep on evolving, we find that eventually the biggest objects start collisionally depleting and the whole mass goes down. And when the mass goes down, well, then we start getting a turnover here as dust gets lost by Poynting Robertson drag. So that's a general picture of what's going on in debris disk. Now let's add some planets into the system. Well, the way planets interact with the disks is solely through their gravity. And you can go and look in any textbook on solar system dynamics and see that the gravitational perturbations of a planet can be split up into three types. You've got secular perturbations. These are the long-term effect of the planet. So you can think of these, instead of thinking of the planet as a point mass, you can spread the mass of the planet around its orbit. So think of the planet as a wire. Then you've got resonances. These are only applied to material that's on orbits that go round, say, twice for every 3 times that the planet goes round, when there's a ratio of integers. So some material will be affected by resonant forces. And then you've got scattering. So it's an impulsive change to the orbits of material, and they have a close encounter with the planet. So before I say how those manifest themselves in the disks, I just want to say a couple of words on how to model disks. Now, you may be familiar with M-body type codes. We heard about the effect of gravitational dynamics from Quinn this morning. But if you just take the radial force of gravity 1 over r squared, then you can get a code off the shelf like Mercury and just say, I've put in a star, put in some planets, define their positions and velocities, put in some comets and just set everything going, integrate the equations of motion forward in time. It's a very easy thing to do. And you get the dynamics, completely understand the dynamics in this way, with the problem being that you can't study debris disks like this because you can't account for collisions between the particles, because if you want your particles to collide, then you need billions of them. And not only do you need billions of them, but when they collide, you need to create thousands of particles in each collision, and then when those particles collide, they create thousands of particles. So it's a problem of numbers. So usually we use some other techniques. I quite like using analytical techniques to think about how the collisions and radiation forces and the dynamical interactions with planets take place. There are kinetic models, which are essentially the kind of model that I just showed you, which is a one-dimensional model which has a bins of particle size. If you extend that to other dimensions, you have particles, bins of particle size, and orbital elements. That's Sasha Krivov has pioneered those kind of techniques. And nowadays, people are realizing that actually we can include collisions in n-body simulations, but you just have to be clever about it so that you don't create billions or don't need billions and billions of particles. And there are kind of collisional grooming algorithms. And we have Chris Stark in the audience, who is the author of one of those models. So those are the ways of doing it. Most of what I'm going to tell you is taking the approach of thinking about it analytically, because this gives you a kind of qualitative feel for what's going on and where the physics comes from. So how does secular perturbations affect the disk? Well, what's what I'm showing you here is the effect of secular perturbations on a Kuiper belt that extended from 20 AU to 60 AU, 100 million years after a planet that is 1 Jupiter mass formed in the disk at 5 AU, and the eccentricity of that orbit is 0.1, and it's inclined by just 5 degrees to the disk midplane. So hardly very extreme parameters. And you can see that this is a face-on view of the disk. The eccentricity of the planet's orbit has caused the structure of the disk to have this tightly wound spiral. And although I started off the planetesimals on circular orbits, so when they collided, they could have grown if they collided at all. After this spiral has swept through, the collisions are going to be destructive, so the planet also stirs the disk, even though it's very far away. So this is 5 AU, remember, and this is 20 AU and 60 AU here. The fact that the planet is inclined, that causes the disk to be warped, because basically the planet makes everything align with its orbital plane, but it does that faster for material that's closer by. And all of these effects are seen in disks. So there's tightly wound spiral structure in HD 14569. There's an eccentric disk in Fomalhaut, and perhaps the most spectacular example is Beta Pic, the disk of which is edge-on and is seen to be warped. And this warp here is at about 80 AU, and it was this warp that was used to predict the planet that we've been talking about quite a lot this week, Beta Pic B, that's in at 9 AU. So this is evidence that these kind of secular perturbations do act in disks. But we know that planets can have highly extreme orbits, so more extreme than eccentricities of 0.1. And this is emphasized by Fomalhaut little b that has an eccentricity of around 0.8. And this shows some work of a student of mine, Tim Pierce, that's been published recently, showing what happens if you have the secular perturbations of a planet that's got a pericenter at 5 AU and an eccentricity of 0.8. You get different structures depending on how inclined the planet is to the disk plane. So if the planet's orbit is in the disk plane, then you just get an eccentric disk, which is quite interesting because it's nested just outside the planet's orbit. But if the planet's inclined even by 20 degrees, then you get this bell-shaped structure that envelops the planet's orbit. So something that you wouldn't be expecting. Even more strangely, if the planet is actually orthogonal to the disk plane, then the secular perturbations do nothing to the disk, and it just remains as it was. So if you looked at the system, the planet can be orbiting out of the disk plane, which affects how you interpret disks. So I would imagine that if you took an image and saw a disk that looked like that, you'd think that the planetary system was in that same plane, and not that it was 90 degrees from it. And if you looked at a structure that ended up looking like this, well, I would imagine you'd think you were looking at a face-on disk and that it was clumpy, and you probably interpret it in terms of planetary resonances. And you think of resonances causing clumps for this reason. So like I said, resonances are just locations where a planetesimal would be orbiting the star, say, twice for every 3 times that the planet orbits the star, and that's what's shown in this movie here. So think of this being Neptune, and think of this being Pluto. I'm not sure if that's going to repeat itself. What's shown on the left is just what you have looking at in the inertial frame. If you look at this on the right in the frame that's rotating with the planet, you can see that this Pluto-like object comes round, and it spends most of its time in these loops just here. So it spends most of its time 90 degrees away from the planet, and that means if you looked at a million objects like this that were all in the same resonance, then you'd see a concentration of them 90 degrees away from the planet. Each object, so you'd see a clump. Each object itself is just dipping in and out of the clump. It just spends most time at that location. The other thing about the geometry of these resonances is that whenever this object gets close to the planet, it's always at the same location around its orbit. And that means that the perturbations from the planet repeated. This repeated action of the forces at the same location can be good or bad. If you look in the solar system, there's evidence of both good and bad resonances. We've got good resonances in the Kuiper belt, where you have lots of Pluto-like objects, all in 3-to-2 resonance with Neptune. And in the Kuiper belt, you have these big gaps, this lack of material in the Kirkwood gaps that are the Jupiter, the resonances with Jupiter. So I'm going to concentrate mostly on these kind of good resonances. So where do they come from? Well, they come from Neptune not starting where it is now at 30 AU, but starting closer to the star. And then it moved outwards to its current location. And as the planet moved out, the resonances moved out as well. So if we show a movie of what happens in that situation, if the planet moves out, the resonances move out, they sweep through any kind of primordial disk. And when the resonances pass a planetesimal, there's a probabilistic phenomenon that material can become trapped in the resonance and then migrate outwards with the planet. And then because of the geometry of those resonances, you find that as the planet migrates outwards, it causes the disk to become clumpy. You can see the characteristic of the 3-to-2 resonance causing those two clumps that are 90 degrees away from the planet. And this has been used to interpret the submillimeter observations of the Vega debris disk and the clumpy disk around Beta Pictoris seen in CO gas. There's a couple of caveats, a couple of warnings with this. The first of these is that this structure wasn't confirmed by Meredith amongst others when they looked at Vega with interferometric techniques. This doesn't mean that the clumps don't exist, but it sets constraints, and it just gives a caution to you when you see disks that have structure that you need these structures to be confirmed to work out what's really going on. However, there's the flip side to that is that if you don't see what you're expecting, it might just be because you shouldn't see what you're expecting. So I don't think the beta pic clump is less ambiguous. Its exact structure is more ambiguous, but the fact that there's an asymmetry there isn't ambiguous. But if you look at beta pic at different wavelengths, you see actually it looks completely different. And all of these structures that you see at different wavelengths are confirmed. So actually beta pic is edge-on. So when I showed you the face-on image of the CO distribution, that's because, as Meredith was saying, we got these CO observations. You have a third dimension to this image. So this is the spatial distribution of CO on the sky, but at each point you have velocity information as well, which allows you to deproject the disk, which is pretty cool. But you see different things when you look at different wavelengths, and that's exactly what you expect. So remember what I said before about how planets interact with the planetesimal disk, creating those clumps. That only applies to the planetesimals. It doesn't apply to the dust. It doesn't apply to the distribution of CO. To understand their distribution, you have to think about how collisions are creating those species and then what happens to them due to the effect of radiation forces, for example. So in the model, you expect to see a dependence of structure on wavelength. So if you have a distribution of planetesimals that is clumpy, you expect millimeter wavelength observations that trace millimeter-sized grains to have a clumpy distribution. But when you go to shorter wavelengths that trace slightly shorter, slightly smaller grains, you expect radiation forces to nudge these grains out of resonance, and so you expect an axisymmetric distribution. If you look at the smallest dust that's getting blown out by radiation pressure, you see this spiral structure, and that's because the collisions happen most frequently in the clumps. So that's where they start their outward trajectories. And the same reason you get an asymmetry in the distribution of CO if the CO is produced in collisions. So that's just a warning that disks are complicated. Okay, so I wanted to come back to this resonance, to the PR drag issue. And I'm going to do this by reference to some of Chris's models. So these illustrate the point that I made before, which is that if the disk is dense, so here we have the same disk with an optical depth of 10 to the minus 5 and an optical depth of 10 to the minus 7. If the disk is dense, 10 to the minus 5, then all of the dust in this system remains fairly tightly bound. It's most concentrated in the source region in the ring out here. However, if the disk is is faint, is lower density, then the dust can migrate inwards by PR drag. Now, there are 2 points to make from this. There are 2 points I want to make. First of all, although the dust is mostly concentrated in the ring, the inner regions are not empty. Some dust always makes it into the inner regions. And there may be some evidence for this. Now, so what I'm showing here is the expected emission at 8.5 micron divided by the emission from the star that you expect from a model in which you've got a planetesimal belt at a given distance, which is characterized by the temperature of that belt here. And this 8.5 micron emission comes from dust that's at around room temperature, so dust that's in the inner region. And you can see, these are the lines are for different spectral types, that you always expect excesses that are between about 0.1% and 1%. Now that's quite a low level to detect photometrically, but it can be detected using nulling interferometry, as Denis was telling us about. And what's shown on here are Keck nuller results from Bertrand-Menesson that are now submitted. These filled-in points are the detections, and the open points are marginal detections. But you can see that these points lie very close to the line that is predicted. And this is worrying. This worried me. I was expecting this plot to show that the level would be insignificant. And it worries me because this level here, 0.1 to 1%, is the kind of level that is very problematic for trying to image terrestrial planets. It might be hard to detect, but it's at a very high level. And this means that the inner regions of planetary systems, if they've got any outer belt, are going to be permeated with small dust. Only small dust, mind you. Very small, fast-moving dust, but they'll be permeated with small dust. So the reason this is a problem is because of its problem for imaging Earths. Denis went over this in more detail, so I don't need to go into it in any detail. But I did like when Gary showed this image of the pale blue dot on Monday. I thought this would be a good way of illustrating the problem for imaging Earths, because this dot is sitting on a bunch of noise. This noise here isn't the zodiacal light. In fact, this noise is light refracted inside the telescope from the sun, so more of the kind of thing you're trying to get rid of by coronagraphic techniques. And in fact, the zodiacal light isn't at the level where you think it would cause a problem for detecting Earths. It's more when it gets up to levels that are 10 times zodiacal levels where you get a problem. As I say, Denis mentioned more about that. But this 10 times level here is 10 times lower than the level that it was detected in those systems that I just showed you. So the news isn't all bad. So the other point I wanted to make from this is that as the dust comes in, if there are any planets in the inner region, then the dust is going to go past those resonances. And whereas before I showed you a movie of how a planet migrates outwards and traps planetesimals in resonance that then migrate out with the planet, you get exactly the same phenomenon if the planet stays still, but the dust migrates inwards because it encounters the resonances and then it can stop migrating inwards. Eventually it falls out and carries on in, but it's going to stop for some time, and that's going to cause a concentration of dust close to the planet. And we know that this happens in the solar system, and also, importantly, that it can happen for very low-mass planets as low in mass as the Earth, because this is a model of the distribution of dust in the inner solar system, and the dust that is trapped in resonances with the Earth, it starts off in the asteroid belt, comes in, encounters the Earth's resonances, and because of the geometry, you don't get the two clumps in this region for reasons I won't go into. What you get is one clump that follows the Earth around its orbit. So this is in the frame that rotates with the Earth. So as the Earth goes around in its orbit, this whole structure rotates around. And this is just a model, but we know this happens because it's been observed. So Debbie introduced us to Spitzer yesterday. It's an infrared satellite. Spitzer was put on a trailing orbit. It's not orbiting the Earth. We're in the L2 point. It's on a trailing orbit. So over the 5-year course of its cold mission, it flew backwards. This is just to zoom in here. It flew back right through the middle of this clump. And if it looked at the brightness of the zodiacal cloud around it, and if you look at how bright the zodiacal cloud was as a function of time, it went up and went down exactly as predicted by the model. So where does this leave us? Well, it leaves us with the problem that exozodiacal dust is going to cause us a problem, with the silver lining that actually, if we detect exozodiacal dust, we might be able to learn something about the presence of planets anyway by looking at those structures. But not all of the systems that have dust is caused by PR drag. Let me go back to this plot here. These can all be explained roughly by PR drag, perhaps. This one up here is an outlier, and this one up here is Eta Corvi. Eta Corvi is a nearby F star. It's got a Kuiper belt that is imaged at about 150 AU in radius. It's imaged at 70 micron, 160 micron, and in the submillimeter as well. But it's also got a hot component, so you can see in the spectrum it looks like it's got two temperature components. It's also been looked at in the mid-infrared, and as Denny was mentioning, there are new results from LBTI that pinpoint exactly where that dust is. It's at about 1 AU, so 2 orders of magnitude difference in radius, and at a level that's very high, too high to explain by PR drag. So where does this come from? Well, if it doesn't come from the outer belt, then perhaps it is produced locally in an asteroid belt. There's a problem, though, and that's this age. So Eta Corvi is 1 billion years old, and as we saw in the first movie that I showed, as you have collisional evolution, you get all the size distribution waving and doing whatever else it does, but eventually the big things collide and the whole of the size distribution drops, and so the asteroid belt gets fainter. So that's shown in this model here. This is just a simple analytical prescription for that collisional evolution. It shows the brightness of an asteroid belt as a function of time for different initial masses. And you can see that however much mass you put into the asteroid belt at early times, by the time you get down to 1 billion years of evolution, it's far too faint. It's 3 orders of magnitude fainter than Eta Corvi has been detected. The problem is if you put more mass in, it just collisionally processes itself faster. Now you might say this model is fairly simple. Perhaps I can change the planetesimal properties and increase the level at 1 billion years. There's certainly some uncertainty here, but 3 orders of magnitude is a problem. Also, whichever way you cut it and change the models, I think everyone would agree that if you have a belt that's at 1 AU and one that's at 100 AU, the one that's at 1 AU will evolve faster. So you would expect, if you looked at the ratio of hot dust to cold dust in the systems that have 2 temperature disks, of which there are quite a few now, then that should deplete with time. And that's what's shown here. And you can see that there is no such evidence for a depletion with time. So it seems like the level of hot dust that you have in these systems is more tied to what there is in the outer belt just by some ratio. So how are these tied together if it's not by PR drag? Well, it can be, of course, in some systems, but in other systems it's not going to be. Well, we've talked about 2 of the ways in which planets interact with disks. There's one more that I haven't mentioned yet, and that's scattering. And scattering in the solar system causes the comets to come into the inner solar system. And when the comets come in, they get heated by the sun, and they sublimate and release dust. That produces quite a lot of dust, probably not as much as the dust that gets contributed by the disintegration of the comet. So they come in, get heated, and they just explode and release all their fragments that then collide and get ground down into dust. And in fact, Nesvorny et al. Proposed that, in fact, the majority of dust in the zodiacal cloud actually comes from comets. I say they propose. This is kind of the problem with comets, is that even in the solar system, where we know where all the comets are, we know where all the planets are, and we know what the zodiacal cloud looks like, we don't know how much dust comes from comets. It's very hard to model dust from a comet-like population because there are so many assumptions you have to make about how the dust gets produced. So we're going to have really big problems to try and estimate how much dust you get in extrasolar systems. The one thing we do know, though, I don't want to to make any definitive statements on this. The only thing I want you to take away is for you to realize what you probably can intuitively understand, that how many comets you get coming into the inner system depends on the planetary system that's doing the scattering inwards. So this is just a model that says you place equal mass planets as close together as possible. How far inwards can you scatter comets? Well, it turns out that if you've got low mass planets, then they can scatter things all the way into the star, whereas if you've got high mass planets, you can't scatter things inwards very far, because the planets, to be in a stable configuration, have to be further apart. So it's harder for them to pass comets inwards. So the only thing to take away from that is that perhaps we can learn something about this dynamics by looking at these hot populations. Now, scattering might cause high levels of comets to come in a more violent fashion, because scattering doesn't just cause the comets to move, it causes the planets to move as well. So if something is conservation of angular momentum, if the comet goes in, the planet must go outwards. And that's how Neptune is thought to have migrated outwards. So you might have heard of this. This is the Nice model. This is a model of how the solar system evolved. We've got Jupiter, Saturn, Uranus, and Neptune. This is time going on here. This is the primordial Kuiper belt. It started off much closer in this model. Everything's just evolving due to these kind of interactions. The planets' orbits are jiggling around until, at that point there, they got pushed into a dynamically unstable configuration that threw Uranus and Neptune out into the Kuiper belt, depleted the Kuiper belt, and threw lots of comets into the inner solar system. And this model was put forward to explain why, when you look at the moon, all the craters are about the same age, about 700 million years after the solar system formed, because in this model you get a large amount of comets coming in when that instability happens. So perhaps we can explain some systems like this, but these epochs of instability are very short-lived, maybe 15 million years. So if we want to explain some small number of bright systems, maybe Eta Corvi, then we can do it in this way. But we can't explain a large number of systems in this way. So where might this dust come from? Well, one other possibility, the last possibility that I'll mention, is that it comes from giant impacts. So we know that giant impacts, so large collisions, happen in the inner solar system. So the Earth's moon was thought to have formed in a giant impact when something the size of Mars hit the Earth. We've got the Hirayama asteroid families in the asteroid belt. They're thought to have been created when the breakup of something very big, a very big asteroid in the asteroid belt billions of years ago. And what's shown on here is the luminosity evolution of the debris that comes out of those kind of collisions. This is the evolution of the Earth-Moon debris. In fact, we don't know how bright it would be, because all of these different lines show different assumptions about the size of the debris that comes off, which we have no idea about. But for reasonable assumptions, the debris is bright, it's above the detection threshold, and it's bright for about 10 million years. Now, I don't want to... The point I wanted to make is not about how bright these are initially, whether we could have some of the systems that we observe being explained like this. What I wanted to use this to point out is that there's an implication of this model, which is that things that are bright now above our detection threshold will eventually deplete, and they'll keep on depleting with a time scale have a luminosity that falls off as 1 over age. And what this means is for every one system that we see above the detection threshold, there's going to be 10 that are just below it, and there's going to be 100 that are quite far below it. And that means that we can use the number of systems that we see above the detection threshold nowadays to extrapolate, to predict how many systems that there will be that will have fainter levels of Zodis. And that's summarized on this plot that shows the fraction is the ExoZodi, what we call the ExoZodi luminosity function. This is the fraction of stars that have 12 micron excesses that are above a given level. So this is what we could detect with Ys. We can only detect excesses that are above about 10%. And this shows the luminosity function that we inferred from looking at correlating Ys with Hipparchus. This is where there are dragons and we don't know what's down here. This is the solar system level. This is the level at which we have problems for TPF. And this dashed line is what you get if you make the assumption that all the things that we see that are bright evolve due to as 1 over age. And that's quite worrying because it means that 50% of stars have dust levels that are problematic for TPF. Okay, we don't have to be worried too much yet because this extrapolation is over several orders of magnitude and we really don't know what's going on. It could be much flatter. This distribution could not be set by evolution. It could be set by comets, in which case it's set by the distribution of comets with the planetary system properties. So that's why we're doing the LBTI host survey to try and measure the fraction of stars that have excesses down at this kind of level. Okay, so that's good timing. So I'm right on conclusions. So disk structures are set by collisions and radiation forces and planets. We understand pretty much how these interact, or at least to some extent we've got some idea of the range of structures that you can get. And usefully, we think we can use those observed structures to tell us something about planets. ExoZodis, well, we're just really learning about these at the moment. We don't know how many ExoZodis there are around, typically around other stars, and we don't know where those ExoZodis come from, but we have a range of possibilities, and we're making some progress at the moment. So I'll just leave it there. Thank you. Okay, so the question was, what happens when you include stellar winds in PR drag? And the answer is it increases the level of PR drag because it has exactly the same effect. So you can basically just increase that beta parameter. It doesn't increase radiation pressure. You only increase the beta that is coming from the PR drag effect. Yeah, well, you can see that the peaks are about the same level, but they're about a factor of 10, so there's a factor of 10 difference. So the inner belt is brighter in terms of fractional luminosity. Can you fit it by a flat surface density distribution? Sorry, I didn't repeat that. So the question was, can you fit the eta Corvi with a flat surface density distribution? The answer is no. So we did that in Gaspar Duchenne's paper, showing how much material there isn't in the middle. So it doesn't fit the SED. I mean, you might have some other process that increases the level of dust that's in the inner region, so there are some trapping possibilities, but I don't think that will work. Drag-induced resonant rings. That one or that one? This one? Yeah. So what's the question is, there's a planet here and there's material here and here. Is the question whether they're the Lagrange points? Oh, okay, so the question of whether these are the Lagrange points, I don't think they are, but Chris is the author of this.
No, so this is the solar system.
Yeah.